we covered some of this in class. Actually, for me it was today, but maybe for you it wasn't today, or it's not going to be today. Some of this already, but remember, to compare acidity, you want to look at the conjugate base's stability, right? So when we want to compare this relative strength of acidity of these two potential acids, what we want to do is to compare the stability of the conjugate bases. And what we said in class, I think, was that this conjugate base, the acetate from acetic acid, is pretty stabilized because there's resonance in acetate, whereas this ethoxide, this alkoxide ion, this conjugate base does not have any resonance. It's not at all stabilized, and so for that reason this is unstable. That means the reaction doesn't want to go to the right, which means this is a very weak acid. It doesn't want to donate its proton because then it would become something that's very unstable, whereas this acid doesn't mind becoming the conjugate base because this is pretty stable. We also wanted to contrast that with this trifluoroacetic acid compound, and that we predicted, even without looking at the pKa value, that we would predict it to be very acidic. And the reason is in this conjugate base structure, the negative charge is delocalized to these two oxygens through resonance, right? That goes like that. But not only that, but the this whole negative charge is stabilized by the presence of these three very electronegative atoms, fluorine. That sucks away some of the negative charges, and so because of that, these oxygens don't feel as much of the excess negative charge. So this is very much stabilized, this conjugate base. That means the reaction would very much like to go to the right, which means this is a very strong and good acid, which is reflected in the pKa. Here's an interesting tidbit. There's more than just 7 strong acids in the world. Like this would be another strong acid that you probably didn't learn about in general chemistry. So I want to add to the last 3 acids that we compare the relative strength of acidity to, and then I want to add this one acid here. It's benzoic acid. By the way, that's another name of a carboxylic acid, common name actually, but I want you to know the name of. That's benzoic acid. Here it is acting as an acid, and if it does, this is your conjugate base. Every time you've got a carboxylic acid that lost a proton and became an anion, that's called a carboxylate ion. This is a type of carboxylate ion, but to name a carboxylate ion, what we have to do is to add 8 ion at the end. So this would be benzoate ion because it came from benzoic acid. Now, here the pKa, if you notice, if you compare acetic acid, it's even more acidic. It's less, the pKa value is even smaller, so it's a stronger acid. And the reason has to do with the fact that this aromatic ring here is slightly electron withdrawing. Okay, and so for that reason, the conjugate base, its negative charge is stabilized by the benzene as well as by the resonance between the two oxygen. Okay, so this is stabilized by resonance, but also by the electron withdrawing group. That stands for electron withdrawing group. All right. Now, with all of that backdrop, let's see if we can rank these carboxylic acids. That's sort of the goal. One of the goals for this chapter is you'd be able to, by looking at the structure, compare the relative acidity of different molecules. So these are the 3 acids we're comparing, and One of these acids, here's a paranitrobenzoic acid. As you can imagine, this has can have a resonance that looks like that. Oxygen picks up some of the electrons from the benzene ring. In other words, this nitro group can act as an electron withdrawing group. Right. So hopefully we see that. What about this benzoic acid? That's a paramethyl benzoic acid. I think we've talked about the fact that carbon and hydrogen alkyl groups like methyl groups, they're actually fairly electron donating. They're rich in electrons and they're not all that electronegative. So this we would call it an electron donating group. That's what the D there stands for electron donating group. So what does that tell us? That means the conjugate base, it's going to have a negative charge. So for that reason, the conjugate base of this, because it's got an electron withdrawing group, should be fairly stabilized. Whereas the conjugate base of this, which has an electron donating group, that would accentuate the negative charge out here because this is electron donating. So that negative charge will be destabilized by the presence of electron donating group. For that reason, we predict this to be the worst acid of the three, this to be the best, and that ranking actually is reflected in the actual pKa if you were to measure it. This benzoic acid, as we just said, it's known to be 4.2. Nitrobenzoic acid, its pKa is known to be 3.4. So that's not surprising. We predicted that to be a fairly good acid. And this paramethyl benzoic acid indeed is worse of an acid than benzoic acid here. All right, let's think about using the acidity or taking advantage of the acidity of carboxylic acids. Let's think about how we might be able to isolate carboxylic acids from a mixture of compounds. Mixture of compound types like amines, alcohol, and carboxylic acids. Right, just like we did with the amines in the last chapter. Okay, we would call this the free acid when it's not ionized like that. That's just a regular carboxylic acid. Because it's organic and it's not ionized, it's not an ion, right? This is more soluble in more non-polar organic solvent than in a very polar water solvent. Okay. But once you treat that carboxylic acid with any amount of base, remember this proton's fairly acidic, it would definitely get deprotonated, and now it becomes an ionic material. This is a carboxylate ion. Because it's ionic, it's superpolar, that means it's very much soluble in water, more so than in organic solvent, which is non-polar. So taking advantage of this, how can we isolate carboxylic acid from these mixtures? Well, here's a cue or a hint. We can treat this with our base. So like, more specifically, we would use something like sodium hydroxide because you can't just get hydroxide ion off of a stockroom shelf. You need to have something like sodium hydroxide. Right? And then what you can get is carboxylate ion. Now, this carboxylate ion, I want you to think with me like which layer it would go into. I don't have a blue marker, so I'm just gonna use black for ether on the top and red for aqueous at the bottom for now. This would dissolve into your aqueous solution. Right? This is going to be in your aqueous. And in the ether layer, we would have amine and alcohol. The amine would stay in ether solution because it would not be ionized in a basic condition. Remember, amines only get ionized under acidic conditions. So in ether, would have the amines and alcohols. Right, in the aqueous layer, you would have the carboxylate. So what do? Well, you can drain this separately. And we're going to collect the aqueous layer only. Okay, so here's your aqueous layer. And it has in it a carboxylate ion. That. All right, and this carboxylate ion, that's not quite free acid. How do we turn that into free acid and isolate it? Well, it's fairly simple. We got to do the opposite of what we just did. If you have a carboxylate ion, if you treat that with HCl, some strong acid, you will get protonated. So that's what we're going to do. But we're going to also add ether to it so we can separate the two layers. So at that point, and if you put all this into your set funnel, of course you're going to have your two layers, and we're going to think about which layer has what. So at this point, this has leftover sodium hydroxide. If you add HCl to it, this is going to have your neutralized material, like your sodium chloride, right? And that's going to be discarded, but we're going to keep the carboxylic acid. That's protonate it back, so that dissolves in the ether layer, and this is going to be what's isolated. Collect the top. So in other words, in the lab you would drain just the bottom layer into a waste, and then you get your top layer drained into another container, collect it and evaporate. Evaporate the solvent, and you get your free carboxylic acids all isolated. So that's how you go about isolating carboxylic acids using the acidity of the acids. All right. I just noticed the last little clip of video didn't get recorded very well. So just to recap what we discussed on this board that you didn't get to see on the video, we said that this Fischer Esterfication reaction, we could call it a condensation reaction, because condensation reaction, its definition is one in which where two molecules that get combined, and then in the process it spits out a small molecule like water. That's a condensation reaction. And this reaction obviously works really well. You guys did it in the lab, but it's very slow without a catalyst. And a catalyst, what does it do? If this is the regular reaction pathway without catalyst, this is how much activation energy your reaction has to overcome to become your product. But if there's a catalyst, the reaction takes a different pathway, or now that we know something about mechanisms, we could say that it goes through a different mechanism, going through different intermediates. And with that, you get to have only just a small activation energy, typically, if it works out. And so with catalyst, smaller activation energy, a lot easier to overcome, so the reaction happens a lot quicker. For example, we could envision doing a Fischer esterification between benzoic acid and methanol, with sulfuric acid being your acid catalyst, and your product would be called methyl benzoate ester, of course water byproduct. And if you make this would have a nice smell, like a minty, nice fruity smell. And that's very common among esters. They typically have a nice fruity smell, and that holds true in the actual fruits. They usually contain esters as the fragrant component of their material. Right. Well, what's an organic chemistry lecture without going through a mechanism, right? Let's talk about the Fischer Esterfication mechanism for that last reaction we looked at a second ago of making methyl benzoate from benzoic acid and the methanol with sulfuric acid catalyst. So, what do you think? What do we think is the first thing that's going to happen? Well, this is an extremely strong acid, sulfuric acid is. So it's going to donate a proton somewhere. And the most productive place to donate a proton to would be this oxygen, and you'll see a reason why in a second. If that sp2 oxygen here, the carbonyl oxygen picks up a proton from sulfuric acid, what you get out of it would be this very much activated electrophilic carbonyl group. So now this is positively charged carbonyl, right? And so this carbon here is very electrophilic. Okay. That means what? This carbon now is very susceptible to the attack by a nucleophile, right? Okay. And there happens to be a convenient nucleophile in this reaction mixture, and that's the methanol. Okay. So methanol, because it has these lone pairs, can attack this very electrophilic carbon that right now is an sp2 carbon. Okay. But after this attack, it becomes tetrahedral. So that's the sp3. Now that becomes an sp3 carbon after the attack. So what's the point? Well, I should probably label this nucleophile. Right. After the nucleophilic attack, it becomes a tetrahedral intermediate with sp3 carbon in the center. And this is very unstable if you think about it. One carbon has not only one big benzene ring on it, but 1, 2, but wait, there's more, a third oxygen. 3 oxygens with tons of lone pairs. Very crowded with electrons. This is a very unstable intermediate. When you form this, this is going to collapse like so. This proton could be picked up by a proton like so. That creates a nice leaving group here. That's the water, okay? Because it picked up a proton, and once that leaves, and it needs to be kicked off by something else like this oxygen, as it forms the double bond, you need to lose a bond. So this is the bond that gets broken, and the water gets spitted out. So this is your collapse of the unstable tetrahedral intermediate step. once that happens, we get to the intermediate that now looks very much like the ester. And we just spit it out water. That's a water leaving group. And once that water, or the sulfuric acid, or I should say bisulfate, that we used at the beginning, if one of those picks up the proton like so, what do we get? We get to regenerate the catalyst, because remember, catalysts do not get consumed in a reaction. And what do we have now? Well, here, once you do that, you reforms the catalyst, but also the product, which is methylbenzoate. Okay. So that's the mechanism of Fischer esterification. And this is a mechanism I definitely want you to master, because it's the foundation for all the reactions, not only in this chapter, but actually in the next, which is a about proteins. It's the first of the biochemistry chapters, but you'll find out that you'll see that this mechanism in play even in that chapter too. So you can be pretty sure that a mechanism like this will find its way on the exam, for example. So that's the end. You guys have a great weekend. Stay safe. God bless you. Love you guys, and see you in a week and a half.